So last time we talked about maximal green sequences, and the motivation for us is to define Dilogarithm identities from these sequences. So today we will first reveal the classical Dilogarithm and the corresponding identities or its other applications in, say, hyperbolic geometry and so on. And in the next class we'll dig into the quantum version of this Dilogarithm function. Alright, so let me just write. So the Euler Dilogarithm function is a very old notion defined by Euler. So this function in terms of a power series is defined to be the sum of c to the n over n squared, and the radius of convergence is 1, so it is defined here. And then it is well known that this expression can be analytic continued to the complex plane with a branch cut. So as in many well-known examples, this will be defined by a contour integral from 0 to your complex point c of the log of 1 minus u over u du. So here will be in this branch cut. So one can plot out the graph of this function, say using Mathematica. This will be the graph. So the real part, as you can see, is kind of continuous on the complex plane, while the imaginary part will have this cut. So this function is a very old function, so the value of some special points are well known, and they are related to the golden ratio. So phi here is the golden ratio, and I think these 8 points are all the points where the exact values are known. So in particular, this is the famous summation of 1 over n squared equals pi squared over 6, because I mean n is 1, then this is Dilogarithm of 1. This function also enjoys several functional equations. So the reciprocal of 1 over z, Dilogarithm of 1 over z, will be related to the function itself together with some elementary functions in terms of the log. And 1 minus c will be of this form. So using just these two relation, we immediately see that if we keep on repeating, keep on applying this functional relation, we see that the 6th expression we have and Li is 1 minus c and Li. So this 6th function will be equal up to just elementary functions. So up to logs or some combination of the standard log. And this is kind of the basis for us to define the relationship between the Dilogarithm functions. Alright, so this is the original definition, but then we can also modify the definition a bit so that some functional equations are nicely satisfied. So for example, one can modify it by kind of removing this term or terms like this. So the corresponding definition is called the Roger Dilogarithms, or the So the Roger Dilogarithm function will be defined by the standard Dilogarithm, but you shift by this elementary part. So here our x range from 0 to 1, and then by definition we have L0 equals 0, I mean not by definition, by continuity, L0 equals 0 and L1 equals pi squared over 6 by continuity, and it also admits a analytic continuation. So the first part is similar to the Dilog, but you incorporate the 1 minus u and u symmetry. So here the z will have a branch cut on the negative reals and the positive reals. So this is the version that we will be really generalizing to the quantum case. And using this function, the well-known pentagon identity can be written in a very neat way. So the following theorem characterizes the Dilogarithm function, the Roger Dilogarithm function. So let's say we have two arguments, x and y. Then the function is unique analytic function satisfying the following two functional equations. The first one is a symmetry between x and 1 minus x, and it says that it equals L1. And the second one is known as the pentagon identity, which means that it has a 5-term relation given by the following. So for Lx, Ly equals the xy term, and then the x 1 minus y over 1 minus xy plus L of y 1 minus x over minus xy. So this is it. This is the characterization of the Dilogarithm function. And actually, we can easily see that the first condition actually follows from the pentagon identity. For example, let's rewrite. So 1 follows from 2. So if we set x to be a over 1 minus b and y equals b over 1 minus a, where say a plus b in between 1, so that this is in a good range, and in good range. And also let's say 0a. That's that one. Then if you rewrite this, then what you get is called the Abel equation. So the second term is b over minus a equals ab minus a minus b, and then the last two terms is actually L of a and L of b. Then finally, if you set b equals 1 minus a, so if you take the limit as a plus b goes to 1, then you will see that by continuity of the Dilogarithm function, you end up with exactly the reflection equations. So this will be the pentagon identity that we will want to generalize later on. So as I mentioned, there are several versions of Dilogarithm function. So this is the Roger version, and other useful one will be called the Bloch-Wigner function in hyperbolic geometry. So let me also review this function, although we are not really going to use it later, but it has interest on its own. So this function is defined to be the imaginary part of the standard Dilogarithm, but you adjust by some, again, elementary terms. So this is definitely not a analytic holomorphic function or analytic function because it has an imaginary part, but at least it is real analytic. So the statement is that this is actually a real analytic, real analytic on the whole complex plane, except at the point c equals 0 or 1 where it is continuous but not differentiable. So using this function, then previously remember that we have the 6 terms here. The 6 Dilogarithm are equal up to elementary functions, but using the Bloch-Wigner version, the elementary terms will all cancel, and we actually have the 6-fold symmetry. So we really just rewrite the previous relation, but now they are actual equality. And furthermore, the previous pentagon identity can also be written using this Bloch-Wigner version. And it actually has a very symmetric form. So in terms of the cross ratios. So the equation looks something like this. So you have 5 terms from 0 to 4. And then the alternating sum of this modified version equals 0 for Ci in the extended complex plane. So here again, the hat means you omit the index. You omit that variable. So this d tilde is a function defined on 3 variables. Let's say let's just use 0, 1, 0, 2. So on 4 variables, and this is defined using the cross ratios of the complex points. Yeah, so in terms of this Bloch-Wigner function, then it actually looks quite nice. So you have 6-fold symmetry, and you also have the pentagon relation in terms of the cross ratios. And actually, this is closely related to hyperbolic geometry. And this 6-fold symmetry really just tells you that the volume of a tetrahedron will not change if you permute the vertex. So to make this precise, let me say the main result by Lobachevsky, which is a very old result in hyperbolic geometry. So it says that the volume of the ideal tetrahedron in the hyperbolic plane, hyperbolic upper half plane, sorry, hyperbolic upper half space. So this is the complex plane together with the upper half space. Whose vertices will be labeled by 4 coordinate, and by definition an ideal tetrahedron should have its vertex lie on the infinity. So the infinity of the bound is the boundary of the upper half space, which is just the complex plane extended by infinity. And the volume of this tetrahedron will be given by exactly this Bloch-Wigner function. So we have this diagram here. So a typical diagram looks like this. So you have an upper half space, so it's a complex plane times the upper vertex, upper axis. Then a tetrahedron is defined by 4 points on the boundary. So here I labeled by C0, C1, C2, C3. And then the edges between each point will be a geodesic in the hyperbolic metric. So a geodesic here will be a portion of a circular arc. Right? So this will span a solid, kind of a 3D solid, and you can calculate the volume under the hyperbolic metric, and the volume is exactly given by this Bloch-Wigner function. So in particular, we have conformal transformation of the complex plane. So these are all the Möbius transformation you can do on your vertex. We can say that the volume of the tetrahedron in the standard coordinate infinity 0, 1, see, is just given by this standard function. So if you have a tetrahedron, you can apply conformal transformation on the vertex, and it will become this simple function without this cross ratio. So all the cross ratios will cancel. And then the 6-fold symmetry that we have seen earlier will just be the same as renumbering the vertex. So it will leave the volume unchanged. Of course, but it may change the orientation, and in that case, the volume will have a negative sign. So you start from the standard tetrahedron, and then you renumber this. So you rearrange the order of these 4 numbers, then you will obtain this 6th expression here, which corresponds to the different ordering of the coordinate, and the plus or minus sign will tells you the orientation. So to understand the pentagon, so now we want to understand the pentagon identities in terms of the cluster seeds and mutations. And this actually comes from some central charge identities from conformal field theory, and related to the some discrete dynamical system called the Y systems. So Y systems really just means the tropical Y seed mutation that we have learned earlier in this course. So given a tropical Y seed, and we keep mutating using these tropical relations, then we can write down actually a more general identities involving the mutation sequence. So let's review the notation. So we start with Y seed. So in our case, we will assume that the exchange matrix is skew symmetric. And let's say the index set is from 1 to n. And we consider the tropical Y seed mutation. In particular, the variables we are considering will lie in the subtraction-free expressions of y1 to yn. I mean, all the tropical Y seed variables will be subtraction-free expression in y1 to yn, and we can actually tropicalize the variables. So this will be our tropical field. So these will be monomials where you just take the minimal of the power when you multiply when you add them. So you basically change an expression from subtraction free to tropical by replacing the plus with the direct sum, or the O plus, which means you take the minimum of the power. So let's introduce some notion. So we say that a Laurent monomial is either positive or negative if it is not 1 and all the exponents of your variables is either bigger than 0 or smaller than 0 respectively. Yeah, so you have a monomial in terms of y1 to yn. So y1 to yn will be the initial variables. And for a general expression y, it is a monomial in y1 to yn. And if all the exponents of these variables are positive, you call this positive and negative otherwise. So in particular, what we learned previously is that the sign coherence of the C vector implies that the tropicalization of all the y seeds we have are actually all positive or negative. Right, because we learned previously in the expression of this tropicalization of the yi prime, the y seed, are actually expressed in terms of this lower part of the extended exchange matrix, and the lower part of the extended exchange matrix are really just it's just composed of C vectors in columns. And so the tropicalization of y prime really is just the monomials where the exponents are the C vectors, and we learned that C vectors has sign coherence, which means that all the exponents are either non-negative or non-positive. So all the tropicalization of these y seed variables will be positive or negative. Hence, we can have a well-defined notion of the sign, just like usual. So we say that a variable is positive or negative if the sign is positive, if and only if the sign is positive or negative. Alright, so one can also write down the mutation of y seed using this sign function. So if you look at the tropical y seed mutation rule from chapter 4 and apply the tropicalization, then we see that the mutation of a variable in the direction of k will be given by the following expression. So it is inverse if I is k, and otherwise it is modified by a power of yk. But you also care about the sign. So if the sign of yk times the sign of b is positive, then you have this term, otherwise you don't have this term. And of course, I mean, this is an abuse of notation, so it really says that you have a seed yi. So this yi may not be the initial one, but you can treat any seed as your starting point, and the B matrix corresponds to that seed, and yi prime corresponds to mutate once on your seed. Yeah, so we will define the notion of a seed pattern. So if I have a mutation sequence like before, then I will let the initial seed to be B1 and Y1. Let me just use. Then inductively we will define the seed pattern B t plus 1 y t plus 1 to be the mutation at the t index. And we say that if we have a bijection or a permutation of your index, then I is a new period of the initial seed if the exchange matrix of the last seed is the same as the exchange matrix on the first seed up to a permutation. And similarly, the cluster variables on the last seed should be the same as the cluster variable on the initial seed, again with a permutation. So, of course, we have already seen many examples of such a mutation, right? For example, many such sequences exist in finite type cluster algebra. Because after you mutate many times, you can always go back to the original seed because there are only finitely many seeds, and this will produce us many examples of new period sequence. Another very useful construction is from maximal green sequence that we learned in last class. So if we have two maximal green sequence, then we remember that if you start from an initial one and then you apply I or you apply I prime to maximal green sequence, then the resulting seeds will be frozen isomorphic. Right. So they are isomorphic up to a permutation of the mutable part. So in particular, we can see, for example, that if you take I and say I prime inverse, so you reverse your mutation sequence, then this will be a new period also, where the new is precisely the frozen isomorphism, the permutation here that you have. So maximal green sequence that we learned last class will tells us many examples of mu period, and mu period can be used to define Dilogarithm identities. So first of all, we have a result that a mutation sequence is mu periodic if and only if the tropicalization of the seed is mu periodic. So this is actually a very surprising fact, because instead of checking and of course and also B. This is kind of surprising because instead of checking the exact expression of y, which y in our original setup is in a subtraction-free expression. So instead of checking a bunch of rational functions, you really only need to check that it is new periodic under the tropicalization, so under the monomial part, the leading term of this rational function. And that is enough to talk about, to determine whether a sequence is mu periodic. Then the theorem about classical Dilogarithm identities due to Nakanishi and other people. So it's a more general version of the pentagon, or it's generalized the pentagon identity. So let I be a period and let n plus minus be the number of positive or negative monomials among all the tropicalization of the seed yk1 up to ykn. So for the first seed we take k1, for the second seed we take k2, and so on. So k is the mutation sequence we have. Okay. So we successively take the corresponding index in the corresponding seed. And so there are n of them, so we count the number of positive and negative monomials, and of course they sum up to n. Then the Dilogarithm function, the Roger version, has the following identity. So either you have the minus version or you have the plus version. And here we take all the yi. Yi means the initial variable to be positive real numbers. So each ykt, each ykt terms, remember, are rational functions in the yi, the initial variables. So we specialize this yi to be some positive real numbers, then this will be the Dilogarithm identities. And of course these two are related to each other because of the reflection equation that we've seen before, together with the fact that m plus n minus is just n. So one can also rewrite this in a single equation. So if we just introduce the tropical sign sequence, so this will be the sign of the corresponding cluster variable, cluster y variables, and we collect them, called the tropical sign sequence. Then the above equation can be written in a single equation. Like this, which is easy to check. So when epsilon is 1, you get the left hand side expression, and when epsilon is -1, you actually get the right hand side expression. So epsilon -1 is this, epsilon plus is this. And then you just add the corresponding signs, and this is a way to write down the Dilogarithm identities in a single expression. So to conclude, let's look at two very simple examples how this equation looks like. So let me try to copy this equation. So for example, when your quiver is just a single dot, so you have only one variable and you mutate at 1, 1, say. So you have one single variable, you mutate once, you get inverse, and you mutate one again, you get 1. And the tropical sign, of course, is plus here, minus here, plus here. So you only have n equals 2 in this case. So this is t equals 1, t is equals 2. and t equals 3 go back to itself, so it's the mu periodic part, and you don't care. You only care about the first two. Then if you just rewrite, then you will see that the first term is L, then you have y1, 1 plus y1 is the first term, and in the second term you have minus epsilon, so minus, and then you have y1 inverse 1 plus y1 inverse, but you also have the epsilon value, epsilon sign, which is minus. So in fact this is the same as the first term, so you get 0. So this is really a trivial identity. It just says that two same expression cancels. Right. So let's look at a more interesting example. The standard rank 2 expression 1, 2, and as before we choose the sequence to be 1, 2, 1, 2, 1. Or if you remember, 1, 2, 1 is a maximal green sequence, 1, 2 is a maximal green sequence, so this is really I and I prime inverse as mentioned. So this is one example where you construct new period from two maximal green sequence. So in any way, so let's look at how we get the tropical expression. So here I include all the extended exchange matrix for you. This is the extended exchange matrix. So I use the version where 1, 2 is -1 and 2, 1 is 1. So because 2 is pointing to 1, and then this is the extended exchange matrix where I mutate using this sequence, and I have the corresponding C vector, which is just the lower part of the extended exchange matrix, and the corresponding variable and the tropical variable. So to get the Dilogarithm identities, remember we want to have the index corresponds to the mutation sequence. So for the first seed we have 1 as the index, so we get 1, and for the second seed we have the second index and we get 2, and so on. For the third seed we get 1 here, so here, and here, so n is 5 in this case. So we have 5 terms. So this will be the 5 terms that we need. And we also want to have the tropical signs. So tropical signs really is just the sign of the C vector. So in this case it will be positive, positive, negative, negative, and negative. So we will have 2 positive terms and 3 negative terms. Let me just write it down. So if I write down the equation of the previous identity, then what I get will be another version of the pentagon identity. So the first 2 will be positive, and the last 3 will be negative. Equals 0. Right, so this will be the pentagon identity, and you may ask whether it is equivalent to the previous well-known pentagon, and the answer is yes, because if I let x to be y1 of 1 plus y1, and I let y to be the second term, then we see that it actually recovers the previous case. So they are actually equivalent identity. So this is the way we deal with Dilogarithm identities. So it turns out that these can naturally be generalized to a quantum version. So you will involve quantum exponential functions, quantum Dilogarithms, and the corresponding pentagon identities, which will be very useful in integrable systems and mathematical physics, where they actually solve the intertwining operator. They represent intertwining operators of representations, say, of quantum groups and things, and these usually will involve this kind of pentagon identities. Yeah, so next class we will start talking about the quantum Dilogarithms and how you can study or understand the pentagon identities in that function. Alright, so that's it for today's class.